Good morning, calculus student today. So I would like to talk about Euler's formula. So the Euler's formula is that's the used one for finding the exact value or the approximation value of y by using the linear approximation with the repetition. Okay, so let's take a look at that, some of the linear approximation, something that we did before. Consider that the functions f of x equals x squared plus 2x plus 3. Find the equation of a tangent line at x equals 1. So first thing that you want to do, so you want to find out f prime of x. So what we found here is 2x plus 2. And then after that, you want to find out f of 1 and then f prime of 1. Okay, so f of 1, which is 1 squared plus 2 times 1 plus 3. So then that'll be 6. And then f prime of 1, which is 2 times 1 plus 2, which is 4. And use the tangent line to approximate that f of 1.2. So let's set up that equation of a tangent line first. So using the point slope form, okay, let me just enlarge this one, just make it bigger. Okay, so what we found here is y minus 6. So that equals the slope, which is 4 times x minus 1. Okay, so simplified it. Then y equals 4x minus 4 plus 6. Distribute minus 4 and then bring that negative 6 to the right hand side as 6. So we got y equals 4x plus 2. So this one is the equation of a tangent line. And then using the tangent line to approximate the value f of 1.2. So y equals 4 times 1.2 plus 2. So what we found here, so y equals 4.8 plus 2, which is 6.8. So that would be the approximation. So is our approximation an overestimate or underestimate, and how do you know? Well, the thing is that if this one is considered a quadratic equation, so the vertex, so any point that it passed through the vertex is going to be considered an increasing curve. So if that's an increasing curve, so any point that's getting further away from 1, so then that would be considered over approximate, okay, overestimate, okay. So this one, because that's the vertex, so x equals negative b over 2a for the original functions, which is negative 2 over 2 times 1. So anything that it passed through negative 1, so the curve is considered increasing. So the one that we're using is at x equals 1. So anything that passed through x equals 1, 1.2, 1.4, things that's getting away, so it's going to be overestimate. Okay? So anything pass, or anything passes x equals negative 1. So f of x is increasing. So whatever the linear approximation that you're doing, so it's going to be overestimate. Okay, so now let's find out the rest of this stuff right here. So we can use the linear approximation method repeatedly to estimate functions value even farther away from x equals 1 as we move farther from the original point 1, 6, by using the larger or the smaller value of x, so our approximation get less accurate. So record that we use the tangent line with point 1, 6 with the slope, okay. So now using the same kind of method, the same kind of process to estimate f of 1.4 by starting with our previous point. Okay, so this one, what that means, started with the previous point, so it's y minus 6.8. So that equals the slope of the previous point. Okay, so using the slope of the previous point, which is what? F prime of 1.2. And then this time we want to approximate that 1.4. So 1.4 minus 1.2. So basically what I'm doing here is just like using that point slope form. So let's find out what that is. So f prime of 1.2. So derivative of the previous point So plugging the number back to the derivative formula, so 1.2, we got f prime of x, which is 2x plus 2. Okay, so this one, that will be giving that f prime of 1.2, so which is 2 times 1.2 plus 2. So it's 2.4 plus 2, which is 4.4. So 1.4 minus 1.2, which is 0.2, and then at 6.8. So for y of 1.4, is that, or f of 1.4, because y is just considered f of 1.4. So multiply this one, 4.4 times 0.2, which is 0.88, plus 6.8. So then that'll be 7.68. And then follow the process, the same process, again, to estimate the value of f of 1.6. So this one using the previous point. So the previous point we have is 1.4, comma, 7.68. So y minus 7.68. So that equals so f prime. Now the thing is that the slope from the previous point. So what I did here, so f of 1.2, yep, the slope of the previous point. This time I need to use the slope of the previous point, which is f prime of 1.4. So x minus 1.6 minus 1.4. Okay, so find out what that is. So y prime, which is 2x plus 2. So find out the slope there, y prime of 1.4. So 2 times 1.4 plus 2. So 2.8 plus 2, which is 4.8. So plug in the number, 4.8 times 0.2, and then plus 7.68. Okay, so 4.8 times 0.2, which is 0.96, plus 7.68. So this one will give you, well, 14, 15, 16, so 8.64. Okay, so this one is just a comparison, just lists that all those number, the actual value, and then the estimate. Okay, so you started off with 1.2. So for 1.2, the one that we found, which is 6.8. And then 1.4. And the one that we found there for 1.4, which is 7.68. And then the other one here, which is what, 1.6. And then we got 8.64. And then you want to compare that to actual values. So this one basically it summarizes that the formula. So x plus delta x, y plus delta y, where delta x is given in delta y, it's given as delta x times the slope at the previous point. Okay, so the formula for doing the approximation with the Euler's method is the following. So x sub n equals x sub n minus 1 plus delta x. Whatever the previous x value that you have, you just want to add the delta x. Then you get a new x value. And then to find the value for y, so whatever the previous slope that you have, you want to multiply by delta x. Delta x is just like x minus, the previous number, okay? The previous x value. and then plus y, the previous y value, y sub n minus 1. So the Euler's method, so this one, the pronunciation is called Euler, not Euler. So you might be wondering why we're using the Euler method instead of using the function. Well, Euler method, normally this one to give you like a better approximations for the tangent line. So let's say that we do have a curve like this. So anytime that we try to do the linear approximation, so once we get this point, so the next position we can use another tangent line. Again, the slope is all based on the previous point. Okay, the reason why that is because this two lines, they're kind of parallel, and then you want to keep doing that so you get another position. So the previous point that you have, and then based on the previous point with the slope, and then you can use that to approximate the next position. So it can be applying for the increasing curve, decreasing curve, could be anything. So let's say that you started right here. So once you get this point, and then you can approximate this position by using the previous slope. And according to the line right here, those two lines, they're kind of parallel. And then this one keep going, parallel. So use the Euler method to estimate that f of 1.4 using 2 equal step with delta x 0.2, and the initial position is 1, 0. So we need to find out the equation of a tangent line started off with 1, 0. So y minus 0 equals the slope here. Plug in a number, so we got 1 plus 0 over 1, which is 1. So 1 times x minus 1. So started with the equation of a tangent line at 1, 0. So we got y equals 1x minus 1. And then based on this one, so we can find out that the next position, so f of 1.2, because the increment for this one is for delta x is what, 0.2, so it started with 0, and then 0.2, 2 equal step. So once you get the equation of a tangent line, so the next one you can find out that f of 1.2. Once you get that f of 1.2, you can find out that f of 1.4. So for f of 1.2, so that means we're using the slope from the previous point. So the slope from the previous point, which is what? 1x. Okay, so basically plug in the number. So y equals 1.2 minus 1. So we got 0.2. Or basically you can just do this. Y minus the previous point, 0, equals 1 times x, 1.2 minus 1, which is the same thing as the linear approximation. So y equals 1 times 1.2 minus 1, which is 0.2. Okay, so it's the same thing. And now the next one that we want to find out is that f of 1.4. So to get that f of 1.4, again, we're using the previous point. So for that 1.2, we got 0.2. So y minus 0.2, so that equals the slope, the slope from the previous point, which is 1.2. So f prime of 1.2. So plug in a number, so x plus y. So 1.2 plus 0.2 divided by 1.2. So we got 1.4 over 1.2, which is 14 over 12. Reduce it, so we do have 7 over 6. And then x minus, so this one, 1.4 minus the previous point, which is what, 1.2. Or just multiply this by 0.2, because that's the difference of the difference of x value, which is delta x. So we got y equals 7 over 6 times 0.2, which is what, 1/5, and then plus 0.2 plus 1/5. So 7 over 6 times 1/5, which is 7 over 30 plus 1/5. You can use decimal, you can use fractions, but it's better to use fraction for this. It's easier to find out what that is. So common denominator, so 7 over 30 plus 6 over 30. So we got 14 over 30. 13 over, not 14. So 13 over 30. And then for 1.4, we find out that is 13 over 30. Another thing is that we cannot use y because that the differential equation is given, and normally with the technique that we learned so far, and you guys haven't learned anything about differential equations, so this one is kind of difficult to integrate it without any kind of advanced integration technique. So that's why we're kind of enforced to do it with linear approximation, but it's a linear approximation with the repetition, so using the Euler's method. Okay, so thank you for watching the video today. So in case I do have any questions, so please, put it into the comments, and then I'm more than happy to answer some of the questions. Alright, so I'll see you next time. Take care.